In this problem, we're asked to determine the output voltage V0 of t if the input voltage Vi of t is given by the plot below. We'll utilize our problem-solving strategy entitled S-domain circuits. So there's our circuit, and our voltage Vi of t is given as a pulse, has a height of 12 and a duration of 1 second. If we look at our problem-solving strategy, step 1 says determine the initial conditions, and if we look at our plot, the voltage source has a value of 0, so all initial conditions are 0. So we don't have any initial conditions. The second step says draw the S-domain circuit. Here's our S-domain circuit. We've got the voltage Vi and of S, and if we go and start doing an analysis, we really need to determine a transfer function. So here's our circuit. So for instance, these two elements are in series in parallel with this one. Let's calculate a ZA. Okay. So now we've getting ready to move in to the analysis stage. So if we look at ZA, then we have 2s plus 2 times 2 over 2s plus 4, which is 2 times s plus 1 over s plus 2. And what we're going to do is I want to go in and calculate this voltage Vx. Now we've got this combined. We basically have a simple series circuit now. That is as follows. The voltage across here is Vx. So now we can find Vx by voltage division. So Vx then is 2 times s plus 1 over s plus 2 divided by 2 plus 2 times s plus 1 over s plus 2 times Vi, and that's 2 times s plus 1 over 4s plus 6 times Vi. So now that gives us a relationship between Vx and Vi. Now if we go back to our circuit, for instance, now we can get V0 in terms of Vx because we basically have just a voltage divider. So V0 is 2 over s plus 2 times Vx, which is 1 over s plus 1 times Vx. So then V0 is 1 over s plus 1 times 2 times s plus 1 over 4s plus 6 times Vi. So then V0 is 1 over 2 times s plus 1.5 times Vi. Now we're ready to calculate V0, but we need the Laplace transform for our input signal there. If we look at that plot, for instance, Vi of t can be written as 12 U of t minus 12 U of t minus 1 volts. So there's a description of VI of t, 12 U of t minus 12 U of t minus 1. So then VI of S is 12 over S minus 12 over S e to the minus S. So then V0 is 1 over 2 times S plus 1.5 times 12 over S minus 12 over S e to the minus S. And that's 6 over S times S plus 1.5 minus 6 e to the minus S over S times S plus 1.5. So now we have our ratio of polynomials, and now we're ready to do step 4, which is perform the inverse transform. So we have V0 of S is 6 over S times S plus 1.5 minus 6 e to the minus S over S times S plus 1.5. So the partial fraction expansion here, we'd have K1 over S plus K2 over S plus 1.5 minus K3 over S plus K4 over S plus 1.5 times e to the minus S. And if we evaluate K1, for instance, we'd multiply through by S and then let S go to 0, so we'd have 6 over S plus 1.5, evaluate S equals 0, which is 4. And K2 is we multiply through by 1.5 and then let S equal minus 1.5, so it's minus 4. Now, our partial fraction expansion then is 4 over S plus minus 4 over S plus 1.5. Now if we go through the partial fraction expansion, this e to the minus S here is just going to tell us, this just tells us it's a time shift. So what we have is 4 over S plus minus 4 over S plus 1.5 times e to the minus S. So all that e to the minus S tells us is that there's a time shift. So now, if we get ready to do the inverse transform, for instance, V0 of t, we'll have 4 minus 4 e to the minus 1.5 t u of t. Okay. That comes from this term. Now, from this term, this just indicates that there's a time shift. So then we're going to have minus 4 minus 4 e to the minus 1.5 t minus 1 u of t minus 1 volts. Okay. So this second term, the e to the minus s, is just the time shift. So we have the time shift here and here.